Welcome to the seminar. So this is the October's Research and Technology Forum of Syracuse Center of Excellence in Environmental and Energy Systems. We're so pleased to have two presenters today, and one representing the academic research, and then the other one is industrial research and development. So we'll start with Professor Dacheng, and he's a Stephen Endowed Professor and also Associate Dean for Research in the College of Engineering and Computer Science. He received his PhD in Chemical Engineering from University of Connecticut in 2003. And then he went to Cornell University for a postdoc fellowship, and then joined the Syracuse University in 2006. Currently, he's the endowed professor, as I said, in the Department of Biomedical and Chemical Engineering, and associate dean for research in the College of Engineering and Computer Science. Dr. Leung has received many awards, including the earlier career awards in Translational Research Award in Biomedical Engineering, and also the National Science Foundation's prestigious Career Award in 2011. Right. And he also received the technique, the Educator of the Year. So he just had a award meeting yesterday. So Professor Leung received that fairly early in 2010. Wow. So, and also he has many publications, many citations, very well accomplished, highly accomplished scholar. So without further ado, let's welcome Professor Leung. Yeah.
All right, thank you, Jensen. Thank you, everyone. He was talking about the awards and things that I know as a professor myself, a researcher. I know we do work day in, day out, but really takes a lot of other efforts for people to recognize your work, for people who nominate the awards, organize events like this. There are a lot of unseen heroes behind things. Working as Associate Dean for Research, I've seen those, experienced those. I think that's really what makes this happen. So thank you for all the work you do and everyone for coming here to see this. So I've been here a few times. Actually, I've been in Syracuse for 19 years. I saw this building built during my early years, and Jensen and others has really made this place a vibrant place. I see a lot more activities. I've been here a few times saying something not about research. So today is about research I'm pretty excited about, also be nervous about to share what I have done. But before I start, I want to acknowledge everyone working here. It's a truly team effort. I'm just here to talk about this, but really took many people over time. I just want to give a little bit higher level summary today. There are really 2-3 take-home points I want to hope you can remember, but not too much about tiny details about things. But this was a collaboration really started during the COVID time. And Jensen called me, I forgot which day that was, during 2020. Well, hey, there's an opportunity working with Honeywell because this pandemic. At that time, I think everybody who remembers those days, you feel like there's something that restricts you about what you can do. You're home, you can't go out. You try to do something meaningful. You see those kind of hero kind of figures, so-called essential workers, things like that, right? You feel like you want to contribute something. So when this came to me, I feel like, yeah, I can do something about this. It's relevant. That would be terrific. So there was an early 2020 to sometime to work on this, and then got the award started. I think it was January 1st, 2021, and last. It's probably still ongoing. Our part is kind of done, but we're still having weekly meetings. I know Jensen is doing a lot more work. I see future opportunity in this. Looking back, teaches us about sometimes you want to be forward-looking before things come, and technology can lead the way. As we all know, COVID has hit us in many different ways. Number of deaths, the number of infected individuals. Now people can put this behind us. I heard that's only 3%, actually less than that. U.S. adults are taking booster shots now. We kind of got used to this almost, right? But the major toll on this has been with us for a long time. And we shouldn't forget this because things will come again. And if you think about how to control this, really come down to understand how this is transmitted and how can you do something different to prevent this. The viruses like this really come through three different ways. One is aerosol, which are fine, tiny particles, liquid carrying the virus, and some bigger droplets that can drop, doesn't travel that far, maybe only half meters or so. Aerosol can go further. But the other bioformat, which is the surface you touch. At that time, I think if I ask around how many of you actually use UV to sterilize your delivery boxes, the surfaces, because we had concern about it, but nobody knew how serious this thing is, right? Do I really have to worry about the format? So these are the things that we try to understand better. And this is important and unique also because there's so many different viruses we experience every day. For kids, usually if you have some sickness, you go to doctors, they will just say, it's just virus. You'll be okay after a couple of days. In fact, we get over with most of them. But the thing that this COVID become an issue is because it can go airborne. And that's can cause pandemic. In fact, if you look back in over the last 100 years, every single pandemic was caused by a respiratory virus, except for HIV. HIV, in some sense, is not the same way as pandemic. It can be called pandemic, usually just simply because the scale of this lasts lingering for over 40 years. We just can't figure out how to make a vaccine against it. All the others are respiratory viruses, last for a few days, but they can transmit so much, and they can cause pandemic. Right? All the other viruses, something more dangerous like Ebola, it never become pandemic because it's so deadly. Before you pass on to many people, you're actually out of this already. So based on the three things that we try to understand, and this project really we discuss about two major questions we try to answer. First one is how does this indoor environment affect this viral transmission, especially for the format, and also the other conditions in the indoor air quality. The other one is can we learn this then help us to engineer better cleaning technologies. So I'll talk more about the first one today because once you know that, you can apply this to different technologies. In fact, there were some tests done by students working with the Dacheng group. Through collaboration, we did that. So to study this, apparently we can't study COVID virus because it's dangerous. We have to find a so-called surrogate. There's something that is safe to work with. It looks like coronavirus, but not the coronavirus. And by reading literature and some other factors, we decided to use the so-called PhyzX. And this is a variant. If you look at the green color is what we chose to use. This is a Syracuse PhyzX. And the red one is coronavirus. They look similar. They both have those spike proteins. That's where we engineer vaccines against about. They are both RNA viruses. This is also important. They're different. They're RNA viruses and DNA viruses. That's their genetic materials. This PhyzX, though, doesn't do anything to human. In fact, you touch it, there's nothing happens. The host of this virus is a bacteria called Pseudomonas syringae. And this bacteria, though, is a pathogen, also doesn't kill human. It kills tomatoes. So if you ever got a tomato with some black spot on it, it's called black spot disease of tomatoes. You usually don't see this in Wegmans. That means they have been sprayed with those pesticides, right? In fact, if you have black spot, that may be good news. You got organic tomato. So good and bad. This one doesn't kill tomato that bad, but it's a host that we can study rather easily. And this virus will basically infect this bacteria and kill this bacteria. So using this, we can study in a very safe environment. And the way it works of this virus, coronavirus, is that it uses spike protein bind to receptor on our cells and then deliver the genetic material, the RNA, into this. And then we use the same machinery to translate this RNA molecule to the proteins that we live on, right? That's our flesh and blood. We need to make proteins. But when the viruses come in, they all use the same strategy. They fool the system. They deliver some genetic materials and host cells couldn't tell. Essentially, you get this, then you think you're making your own proteins, but you're turning this nice kitchen into a bomb factory. You're producing virions. And the virions propagate essentially to be enough to kill the whole cells and move on. And that's how the transmission works. So to study this, then we'll use this surrogate, which is PhyzX. It's doing similar thing, just in that case, it wouldn't be a human cell, but rather bacterial cell that we can study. There are two things we study. We can study viral load. We can study infectivity. Just before I say that, I just want to emphasize the viruses, strictly speaking, they're not living things. They're not like human or bacterial cells. They can live on its own. Viruses are basic materials. You put them on the table, they don't propagate. If they don't have a host, they can't replicate. So this thing is not really a living organism. It's actually bizarre to think that way. So some people say this virus remain alive on the surface. Scientifically, that's actually wrong. They never live as an individual. They live in a host. So we call this infectivity rather than viability. So you can't kill a virus, you can destroy a virus, just to be clear about that. So how do we study this? Then we want to know how many viruses are in the sample. We use the so-called viral load. It's the same way that we study for the COVID test. In fact, through this project, we bought this machine. It's actually rated for COVID testing as well. The test is the same way as COVID test. Essentially, we take this RNA material, design some kind of molecular probes to amplify this. Let's skip the details, but you produce this kind of so-called standard curves. So you know the signal, you know the viral load, you build a standard curve, then you have unknown sample you can study to tell how many viral copies you have of the virion in there. But this doesn't tell you if they're infectious or not. They could be destroyed, but still have the materials in there. Just like people may be tested positive after COVID infection, you're no longer symptomatic, but you still can be tested positive, right? So that's a viral load. The other thing we want to know is actually, is this still infectious? To do this, we essentially repeat infection in this case, because we have surrogate to work with, we don't have to worry about the true infection. This one, the host, again, this is bacterial cells, right? So what we do is you basically just grow the bacteria along on a surface, then you dilute your viral sample, you load on the surface. Once you have enough viruses in a droplet, you can infect the bacteria. When the bacteria are killed, you create a clear spot in that location, but the rest of bacteria is still alive. So you can have a, basically it looks like this. If you can look at carefully, this is the original plate. We have homogeneous cover almost of bacteria on the surface. Once you have the virus dropped, you can see that some areas become clear. And then if you dilute this enough, you can end up in those little tiny spots you can count. Each one of this is an infectious unit. We're called plaque. So we call PFU, plaque forming units. That's how people call viral definition in terms of infectivity. So we look at two things. How many viruses are there based on the RT-PCR, the same as we do COVID test. And then we look at the infectivity of the viruses using its natural host, in this case, is bacteria, by Pseudomonas syringae. So with that in mind, we started to answer our questions. We tested different samples. We need to develop a method first. First is about surface sampling. If you sample surface, we have choice of different things. You swab the surface, and the material is a choice. Is this accurate? Is this representing the surface you're sampling? So we need to look at this different sampling methods and to look at the viral load and infectivity. So first we look at the several different sampling methods using polystyrene swabs, cotton swabs, or this is called a super desk. This is actually the filter we buy from a surface from a company. You can see they pretty much retain entirely the viral load. They can pick up this, except this one has a little experimental error. Sounds like it's higher even than the theoretical amount. This is common. I think when you work with the air quality with the physical experiment, your error range is typically small. When you talk to people with a biosample like me, they'll say, yeah, this is all normal. This is just all, is in fact, it's the way it is. Just like us, everyone is individual, different, and cells behave a bit differently, and other things too. So, but by and large, this means this surface can sample the surface, the materials. However, we found something interesting that if you take this, so the viral load is common, but if you look, they're all okay. But if you go to infectivity, we found this among the sampling materials, this polyester, which is hydrophobic material, we found infectivity dropped by multiple logs. That means the vast majority of viruses were destroyed by the surface. There are a long story we can discuss deeper about this, but basically, you don't want to use hydrophobic material to sample surface wiping of virus in terms of infectivity. So we decided that concluded from there that we should use cotton swab if I have a surface to study. The other thing is about to study the indoor environmental factors in this, especially humidity. So typically the field has been studying things mostly using those small chambers. So this is a chamber in Jensen's lab. We collaborate. This is a 50-liter benchtop small scale chamber. You can control humidity in there. The current of state of art in most of studies using this kind of chambers, you put the surface in there, you can tweak the humidity, you can tweak the temperature, you study viral load, viral effectivity in there, you can draw conclusions in, hey, if I control the indoor environment to be this humidity level, I can see this kind of effectivity. However, this one has limitations because you put the surface here, like you're baking your cookies almost, right? You can only load liquid droplets on this. You can't study aerosol. You have to load just tiny droplets on this. They're much bigger than the aerosol, right? So you have limitation. It's okay to study droplet. But if you really want to study how aerosol transmission affects this, you can use something like a full-size chamber. That's also Jensen's toy. This is 29 cubic meter walk-in chamber. You control humidity, you control temperature. There's a fan blowing, you can mix the air in there. You can sample, you can put a mannequin, you can mimic the environment. And in this case, we put different sampling spots. The spray is from the top. You can see, I don't know if this, yeah. So from the top, you spray this, you generate aerosol, and then you sample in different spots. And then we can still serve cookies to this mannequin, the materials, and you put there, you can study when the droplets, when the aerosol lands on the material of interest, how the viral load and infectivity change based on the indoor humidity and temperature. That's what we can study. So we did first, we look at the viral load and we look at the infectivity by large. Remember I said with two-fold range, this is typical for biological samples. So by large at different locations I just showed in the previous one, in those different locations, they gave rather similar viral load and infectivity, except for one spot, which is number 8 feet behind this mannequin. We think this because the mannequin blocks some of the airflow that caused some artifact there. But by and large, this means in this indoor air chamber, air is well mixed, then you can study humidity and temperature and the effectivity, their effects on the viral load and effectivity. And then we also try if we increase the viral load in the spray, can the system respond, give us higher viral load, higher infectivity? In fact, it happens when we increase this, you see this, both viral load and dark green bar shows infectivity where the number of infectious variant increased with that dose. So this is all good news. And then we study how do we sample this? Sample the airborne aerosol and viruses. We need to get air out of the chamber. So using a sampler we can buy from commercial sources, but you do need to optimize the conditions. So about decision to be made are how long do you inject this virus into this? How soon do you sample? How long do you sample? How do you control the flow rate? All those parameters need to be characterized. So long story short, we tested different sampling time. There's a little busy curve, but what we found was essentially there's an initial decrease in infectivity because you inject the virus from a liquid sample into airborne condition with rather drier air in that case, even there was a 45% humidity compared to a completely aqueous environment. There is a decrease in infectivity, but after that, the curve plateau. The good news is that we just need 15 minutes to sample the air. That gave us enough time to do different conditions basically on the same day. Right? So we picked 15 minutes as a sampling time. The other one was the flow rate. So there's a flow rate of the air going to the sampling liquid to collect the viruses. And if you increase the flow rate, of course, you can increase the contact time, increase the contact with the liquid so you can capture more virus. But increase of flow rate also increase the shear, right? The shear can potentially affect the variant structure, so can potentially lose infectivity. So we need to optimize this maybe. So we tested this at different conditions. So this sampler is rated to go up to 12 liter per minute flow rate. So we tested from 4 to 11.5, just to leave a little room there. What we found is the lighter brown bars shows the viral load, basically how much viral particles you can collect during the sampling time. And then the darker brown bars represent the relative infectivity. What percentage of the virus you collected are still infectious, meaning they're still functional, not killed by, not destroyed by the share. So we saw that the flow rate didn't have major impact on the infectivity, but if you go higher flow rate, you do have significant increase in the viral sampling efficiency. So we decided to go with a higher flow rate of 11.5 liter per minute to sample the air. All right, so now we can have this figured out. We can sample this by controlling the temperature and the humidity. We're more interested in humidity because indoor room, you don't really change temperature that much. So we keep 25, and then we increase the humidity from 25% all the way to, I think, 87. So here's what we observed. This what is typically the field called a V-shaped curve. This has what means is that if you look at the relative humidity in the environment and you look at the viral infectivity, it follows this V-shaped curve, which means when you increase the humidity, the infectivity of virus actually decreases first and then increases again. So this typical V-shaped curve has been shown using the small chamber experiment by adding droplets. But this is the first time we prove this also exists in aerosol transmission in the indoor environment. And there's also time dependence of this because as the time drags, you will see the virus loss its infectivity gradually. The viral load didn't change with humidity. That's expected, right? So by increasing this, you can change, if you change humidity in the room, you can make the virus less infectious. That's important to know. And we found the minimum point where the most effective humidity level was 75. So if in the winter, probably that means in the winter time, if you have virus in your room, in your house, you increase the humidity higher than just outdoor 20, 30% will help you inactivate the virus. So there's something new about this finding. And we also look at this, likely this inactivation at this early point follows first order kinetics because decays exponentially. At 75% humidity, the decay rate is about twice compared to 45% humidity. Another interesting thing, what we found was this actually very different than previous knowledge. This regarding the porosity of materials. So the field has been thinking, or in general, has a conclusion that when you have a more porous materials in terms of format, and the virus infectivity will decrease, would have lower infectivity on porous materials than non-porous materials. Non-porous materials such as glass, stainless steel. Porous materials could be this drywall, for example, or some cloth, right? So that's what the field says about this. What we found, though, is if you do this aerosol transmission study, we have different materials with different porosities. There was actually no difference at the same humidity level in this aerosol transmission compared to the droplet people have done before. And we proved that too, that so first we show this aerosol, the viral load didn't change in terms of the aerosol transmission, right? So you can load the same, you still have the same amount of load. That should be, if you have different materials on the table, the air just drop less, right? You have the same load, but infectivity didn't vary with the porosity as you would observe with those droplet samples. And you can see the left one is in the small chamber. This to mimic what literature typically does in those surfaces. On those surfaces, you load droplets, you look at infectivity. We found this, for example, this uncoated wood, there was no detectable viral infectivity on that material. And the theory behind this, there are a lot of discussion literature. In general, it's believed that because it's porous, so the liquid can go in. Once the liquid goes in, there's an interaction with the material that can cause the droplet to dry and evaporate. That complex interaction then indirectly affect the infectivity. There are a lot more into that. But what we found, though, is if you precondition the material, porous or non-porous, with this humidity in the room, if then you have this aerosol landed on that, then the local humidity by the air dominates that effect. Essentially, it's not about porosity, it's actually about the local humidity affected by this ambient humidity for aerosol transmission. And that's the dominant path of transmission. So that's certainly important to know. Then we verify that, for example, we look at the pores. Indeed, they have different pore size based on materials, but they didn't show the same change once you go aerosol. So just take home message. I think there's something I don't want to read this, but essentially we did some study with this. We're happy to see we can take very safe surrogate to mimic a pandemic causing virus. And then we found there are different ways to study this, but it's very important to study aerosol transmission rather than just droplet. That requires a more controlled environment that's feasible. I think the throughput of this is still low. It costs a lot of money, a lot of time to test this. So the future direction could be something more integrated with computational tools and experimental tools to do this, not only to detect this, the variant in this, but also help us to predict how these parameters can change. This can then also inform some HVAC strategies you can control for your viral transmission prevention in that case. So, so with that, I want to thank Honeywell, my collaborators, and also a lot of work I discussed today was done by Alois, who is my PhD student, going to finish pretty soon. I don't know if I have time to answer. I think I do. Sorry. Thank you.
Questions? Go back a couple slides. There was something you said that, keep going. Keep going.
This?
So there was a comment about so there's a comment about how when you're trying to pick up the virus with hydrophobic materials, how does that kind of blend in with this porosity observation?
Oh yeah, that's a good question. Actually, the later results wasn't about the sampling. I think there may be some confusion. I did the sampling first when we tried to sample, for example, in the room on the wall. So we did that. But later when we did the materials, we actually just cut them into 1-inch coupons and put in there. We didn't do swabbing, but I do want to share that data because if you actually go out and sampling, I think it's important to know. So sorry if that was confusing, but there are different kind of experiments. In this one, there was no swabbing.
So you just cut the materials, put it in there for evaluation?
Directly just test it, yeah.
Okay, so for what reason would you not see a similar, you didn't see a similar observation then?
Between the droplet and aerosol for this setting, yes, we didn't. I think the reason is because when you have a droplet on the surface, you have more liquid in there, right? And this liquid gave virus protection differently than the aerosol, which has a very tiny amount of liquid, evaporates very fast. So if you land the virus on the surface with aerosol, essentially they become dry condition pretty quickly. But if you have droplets, it's going to stay in the aqueous environment longer. And then the surface hydrophobicity, porosity, physical characters will have different interactions with that droplet. That will introduce a confounding factor in some way to say, and evaporation and condensation and all the other things will really affect the infectivity there. So it's just different environment. I think that's, if you realize that, then the result wouldn't be surprising. But the true mechanism behind this requires a lot more investigation, of course. But I think it's certainly important to notice these two are different conditions.
Okay, great, thank you.
Question.
Yeah.
About the infectivity of the virus. Okay. Is it more affected by the physical force or by chemical?
You mean to destroy the viruses?
Yeah, destroy it.
They're equally important. I think in many cases, the chemical force probably would be more effective because this variant looks like they're whatever you think they're powerful or dangerous, whatever. Essentially just small bag of protein stuff and some genetic materials. They're very fragile. So if you have, for example, that's why this hydrophobic surface can actually be antiviral in some sense. And if you have a charged surface, it can be antiviral too. So a lot of this would be. But if you want to physically shear this, for example, I did mention shear, right? But the virus and bacteria in general, they're much less sensitive than shear because of their size. So they wouldn't experience the same kind of shear or forces as we experience. You can make a simple analogy that if you go to a state fair, you take those rides, probably young people can still do it, right? Even that is, you feel pretty intense. In terms of G force, that's just about 1 to 2 G. But you can be killed by 5, 6 Gs. But the microbes, even bacteria, they're 1,000 times bigger than viruses. They can tolerate 10,000 G. The viruses, centrifuge force, and things like doesn't matter. So I think eventually it's just about what happens on the very surface in terms of chemistry and physics. In general, probably easier to apply chemical forces than physical forces to that thing.
It's like alcohol.
Oh yeah, alcohol basically, yeah, you melt the membrane, right?
Chemical.
Yeah, that's chemical, right?
The other question?
We studied the temperature as a factor for this activation.
Yeah, we didn't study temperature, but certainly will have effect. I think higher temperature will be antiviral in general. That's a common thing that coronavirus, once you go to summer, well, a lot of viruses, when you go to summer, they disappear, sort of, right? Because there's more outdoors, people go outdoors, that's one thing, but higher temperature usually make them less infectious. But we didn't study that because we want to focus on indoors.
Yeah, like stable around like 22 degrees.
At 22, yeah, this was 25, I think, right? Jensen was about 25 degrees Celsius, plus minus a little bit.
Thank you for the presentation. My question is, what is the mechanism of causing the inactivation changing with the RH?
Yeah, we think the virion has the spike proteins and the envelope. This is an envelope protein, envelope virus. For those to remain active, they need certain chemical environment. In general, if you take the cells, put in just pure DI water, they don't do well, right? The virus is a similar way. It's called osmotic shock. So there's ion concentration inside of this need to be balanced by something outside. So the liquid is important for all these things. And if you dry this, humidity probably like that, you can dry this. And then also when you have higher humidity, that can also affect how this, or basically humidity in general can affect how this virus interact with the surface. Hydrophobic, hydrophilic, how would that change the shape of this deformation, things like that would indirectly affect this integrity of the virus and then the infectivity of it. But some of this, quite honestly, are still unknown. But even if you have aerosol, you sneeze, for example, when we have saliva out, saliva is not just water. There's actually salt in there. So when this dries, the salt can crystallize or form even just precipitates. And that too can interact with the envelope of the virus and can cause damages to that. So again, I think they're more sensitive to chemical environment than the physical forces in general. Sorry, I don't have a clear answer to that. It's not entirely no. Good question, though.
Seemed like your highest concentration was when you were at 25% RH. Why didn't you test on lower humidity then to see if it went up even higher?
I think that's partially because of the chamber limitation. Maybe Jensen can answer that better.
But I think, well, the project is more for indoor environmental application. Very rare. Humidity is close to 125.
Right.
No.
Okay.
I think there are studies that show the lower.
Yeah.
And reshape Thank you.
All right. Thank you.
So next I will actually introduce Tom Dunbar. DOE lab when the first time met 3 years ago. Technology, but it is very, I was very impressed by this energy we get in Washington. Right? So he's the founder and CEO of tomPhyzx LLC. He has several inventions. Today, we talk about innovation.
Yeah, so we've been working on another approach to that was instigated by COVID as well, is how can we use ultraviolet light to inactivate pathogens in the air? And so that was the basic premise, which I can get going here. So it stems really from just the fundamental physics of radiometry. So if you consider this image here, the idea is we're looking at light, so these photons converging on a point in space, and they're coming in from all different directions. And so what we're interested in is what is that characteristic at that point in space. So from fundamental radiometric text, you get definitions, energy within an optical field, energy density is you look at how much of energy there is within a volume element. And we've taken that just one step further and said, well, what we really care about is the power density. So all of our work really centers around this concept of what's the power density at a point in space where that viral particle may be because it's in the air. So we took this device actually twice down to North Carolina to the Research Triangle Institute, put it in a chamber, interjected viral particles. We were using MS2 as a surrogate. So the black line is basically a particle counter inside this cavity. And the green line there is we take samples over time and show how many of those particles are still active. So our first shot was not so great. The second shot, we ended up getting a certification that was a higher number than the device was operating. So we were kind of uncertain as to what was going on, but we knew we had a device that within 20 minutes, less than 20 minutes, we could clear the air in this particular space. So we knew it worked pretty well, but we really didn't have a means to understand what was happening on the inside of the cavity from that power density standpoint. So joined the partner program, got a project, worked with Dr. Ren to investigate a much more difficult pathogen. So we picked an agricultural pathogen, a mold spore. Mold spores are bigger. It's covered with melanin coating, so the light has to get through that coating. It's basically very tough. And what we did is we inject pathogens, then we sample, then we go through the device, we measure the flow, and we sample again and see how we make out. And we tested 3 different things. We tested the standard unit, which is what we took to North Carolina. Didn't do so well against the mold spores. So I turned all the knobs. I built a device called the Theta Max, and we did fairly well, quite well. And then we backed off a little bit. So I had 3 devices that we now have an idea on how they interact with these mold spores. And to kind of cut through the full thing of it, you can see with the standard unit, we've only got about 24% inactivation rate. So what the mechanism is that photons are absorbed into the DNA molecules. They form a chemical reaction. It creates a dimer. It puts a kink in the DNA, and it can't replicate. So that's basically what's going on. So we only got about, so we slowed the air down, gave the pathogens more time in the chamber, and we got about 40%. We weren't happy with that, so we turned it up to the bigger device, and at 130 CFM, we were getting less than 1% survival. So very happy with that. So I pulled the parameters back a little bit, and we still got less than 1% survival. And the same kind of a thing. So you have the samples at the input side and the samples at the output. And, you know, we're just nothing, you culture that, and we weren't getting anything out of there. So that was the approach. But both of those didn't give us an idea what's going on inside. So I started another project to build a detector that I could put inside the device and measure that power density. That's the goal. And so we built that device, and here's a prototype of it here. It's essentially the key component is a little quartz sphere. The light enters the quartz sphere, goes down through a light pipe to a photomultiplier. The photomultiplier is sensitive to the UVC range. And so we get a photocurrent that is proportional to the photon density. So now I've got a way that I can measure this. Over the course of this project for about 1.5 years at Cornell, we went from a substrate which had about 5 orders of magnitude of non-uniformity. And what I mean by non-uniformity, this little image is a test facility. The sphere is in the center. This is an array of UVC LEDs that I can slide around that ring. So I can put it up at the top and understand how that light is received. And then I can move it over here and see how that's doing and move it around. So I use the global technology. So looking at the top is -90 on latitude. The equator is 0. And so that's going right in the side. And then coming up from the bottom is 90. So we can't get all the way around, but pretty close. So over the course of 1.5 years, tried a bunch of different things. I'm now actually carving openings in an aluminum coating on the quartz sphere. It's kind of a fun project. And I built a device that was about plus or minus 40%. So at this point, I said, okay, let's look at the devices. Let's actually make some measurements. And so these are the first measurements. So this device right here, that's about as close as I can get to the light source. And what's important to recognize is I use that value to compare everything else. So this is just the light. This is just the light source. It's not in the device yet. So the goal is, how much better is our device than just using the lamp? And so this is the number that we really are comparing to. And you can see I've got a reading on the picoammeter, high voltage to the photomultiplier, and we make this reading. So what does the lamp do by itself? So now what I've done is I've gone from that location that you saw in the image, and I've just moved away from the lamp. So how does it fall off, right? Well, we know fundamentally that light falls off like 1/r². If it's a point source and you're moving away, but this is an extended source. This is a long source. It's 5 feet long. So you get contribution of 1/r² from places along the source. So this is the numbers that we have. So that's the lamp by itself. Now, how much better is it when I turn on or put it inside and now measure the cavity? So this is the data from the standard cavity. This is what we took to North Carolina. This is what we know does a pretty good job against MS2 at 150 cubic feet per minute. So I now have got some data that relates to the biological result. Very important. Then, okay, that didn't do so well against some mold spores. What does the larger device do? And so putting the larger device data on there, I get a dramatic increase. Now, it's important to remember that these numbers are all, what was that first one when I was laying right next to that very intense lamp? That was this number down here. So in my standard unit, I'm getting values bigger than that for most of the cavity. In fact, up here, any place I go, and so I'm going from the lamp to the sidewall of the device. So anywhere in there, I'm getting values larger than if I was at the surface of the lake by itself. So then reduced the parameters a little bit, and I now call this the lab device. And what's interesting here is that I'm actually getting this to turn up. And I know if I tweak this a little bit, I'll be able to get what is almost a constant photon density on a cross section through that. And that's huge from the standpoint of investigating what happens to a pathogen that's going through, right? If I have a air sanitizer that the pathogens can go close to the light, they're going to get a different response than if they're way away from the light. Here, in this device, it doesn't matter where you are in that flow going through. You're going to get the same hit by this light. This is huge. So those are the data that we took. Just to give you kind of an idea of the scale, I mount this thing to an XYZ positioner so I can drive it around inside. And that's the max unit, about this big around. And I can get a ways inside there. I do know that the further I go in, the numbers come up a little bit because I'm further away from the exit port. But that's a very slow incline, and the uniformity is still pretty good. So 2 devices there. I call this thing the Optosphere, and now that's Theta Max. That's our larger device. Okay, so what's going on? Why is one better than the other? So I've developed this concept called the principle of same time. And what this means is that if you have a continuous extended source and you want to know what the density is at a point in space, that density is the combination of all of the photons that arrive there at the same time. And so if I look at a section, so here's the outside wall of the unit. There's the point I'm investigating right here. And I look at the shortest distance to the source. So light leaves the source and it takes a little time to get to that point. And we know that it's going to fall off at 1 over r squared as it goes from there to here. So my time values are negative, and these are all just numbers for demonstration. There's no units or anything. It's just to make the curves work, basically. So this is the 1 over r squared fall off as it travels to this time 0, which is when it reaches this point. Okay, so that's just one point on the source. What about other points? What happens with them? We know this one's going to show up first because it's the closest. Okay, so if I go further away, that's the trick. So here I've gone further away. So I've moved down the source. And from that source, now I've got to travel a longer distance. It's going to take some more time, but I've still got that 1 over r squared fall off. At the time equals 0, I just need to add these two up, right? And you could say, well, there's points all over that source. There's straight line shots from basically the whole top section of this circular tubular source. I mean, that's a really ugly calculus problem. And I've done some work trying to solve it numerically, kind of convinced myself maybe I'm right, but it's really not about actually doing that. It's about the theory behind that. How does this work? Okay, so there's a couple of rays. Now there's another approach to get to that point, and that is to go up and hit the reflector and bounce. So that's the next one. So I can go from this to hit this surface. So the green part really, I've done this or attempted to do this where the two lengths are the same as the distance away. So it's following the same curve. It's left at the same time, in other words. So this light is left at the same time as this one. And for the first leg of its journey to the reflective surface, it follows the same 1 over r squared fall off. Now it's going to hit that surface and it's going to reflect. But the reflection is not perfect. In fact, that's a big factor. How reflective is that surface? If it's only 40%, that's not as good as if it's 90%. So what happens when I hit that? As soon as I hit that surface, I get a drop. And this is, again, numbers just to show. That's actually a 40% drop, but let's call it 90. So we know what's going to happen. It's going to reduce a little bit. It's going to end up getting there, still following the same curve. So this is a reflection that is specular. And to put things in perspective, my standard device is a specular reflection. So when you looked at the data from the specular reflection, you could see it was about a factor of 2 gain. But what if that surface is diffuse in reflection? What happens then? Well, it acts, you still get the drop off, but now it acts like a new source. And so it starts out with a 1 over r squared fall off. It follows the green curve, and its contribution is dramatically less. However, there's a lot more places that can occur. And this is why the diffuse reflection is so much better than specular, because the specular reflections require that it fits the law of reflection, which means angle in equals angle out. Diffuse, all you got to do is hit the surface and you get all the angles. So that's what makes that so much better. Okay, so this introduces a concept I call flux capacitance. What this is a graph that demonstrates the contributions. You add them all up. You add up all the ones that got there at the same time. and they leave at different times to get there. And so if you look at what those differences in time are, you get a curve that looks something like this. And the curve, and I don't know exactly what the shape looks like, but I know it's a factor of the geometry of the cavity. I know it's a factor of the reflectivity. 90 is better than 85. I know that it's a characteristic of what's the source look like. You got a tubular source, you got an LED. What have you got? What's your source look like? And where you are in the cavity. And so you add up those things and you get the flux capacitance, which is proportional to this area. If I multiply that by the photon density at that maximum point right on the surface, I get what the photon density is at any location within that device. So these are the components of the concept that get us to important applications. So what do we do with this stuff, right? So we don't have a good understanding of how pathogens are inactivated in the air. There's been a tremendous amount of work done in Petri dishes where you have viral distribution on a Petri dish and you illuminate it with UVC light and you figure out what is inactivated and what's not. Lots of work done that way. Very, very little has been done in the air. So if I have, this is the same device that we used at our project last year. If I have a uniform reactor, so what I mean by that is instead of photon density XYZ, it's approximately photon density in the Z direction. So because remember, I've made it constant in X and Y. So I can take that and I can, knowing the time it takes for a pathogen to get through the device, I know what the exposure that has been impinging on that pathogen. So I now know this number. I can do a biological test where we figure out what the survival is on a single pass, and then we can calculate what the decay constant is. So this as a product by itself is a research tool for us to really get a better understanding of what's going on with pathogens being hit by UVC light from all directions. So that's one application. We've did a project with an NSF I-Corps program where we looked at our technology and came to the conclusion that the controlled environment agriculture was a good application. Controlled environment agriculture is growing stuff in a box, basically. So I just clipped a couple pictures. This is a shipping container. And so people have been trying to do that. They're trying to grow stuff all over the planet in environments that are not, it's too cold. So how do you grow strawberries in Montreal? Kind of a thing. So how do you adjust that? So we found that their biggest problem is energy. In fact, a lot of the controlled environment agriculture in Europe right now is going out of business because their energy costs went up. So energy is huge. And when you have these closed systems, the heat that's generated from the lights raises the temperature inside the box. And so we've got to take that out through a air conditioning unit to cool it down. And that's a big energy cost. So why don't they use the outside air? Because they're concerned about bringing pathogens in. So if I can sanitize the air going in, I can dump the heat going out and bring cool air in and reduce the energy costs inside this device. You produce a lot of oxygen when you're growing stuff, and you lose your CO2. So they have to add CO2 to their systems. If I bring in outside air, it's already balanced in CO2. So there's a couple of factors that we really think we can help this technology or this market segment out. And then this previous summer, we started to look at another characteristic of our technology is that we move the air. We want to make the air flow in the room such that the cleanest air or the most recently sanitized air is provided to where you would want it. So we did a study here. Professor Tong helped us with this. And this is a simulation of an upstate medical hospital room. We have a patient laying in the bed. The patient is emitting a virus. And what we're trying to do is we're trying to move that virus away, because if you're sick, you have these shallow breathing. And so we want the air to be moving past your face to carry that air away. And it's a really early on picture I just clipped, but we could see the air from the device. So our device over here is against this wall. It takes the air off the floor. So it goes in down here and it sends the air out there. It goes across the ceiling, down the other wall, and comes across the patient laying in the bed. So we were looking where that air goes. And also we got 5 doctors standing around. We're trying to figure out which of those doctors is in the wrong spot, because one of them may be in a place where the viruses that the patient is emitting may be coming right to them. So don't stand at the end of the bed. Just saying. Yeah, so we're just getting started on this. We're going to extend this project. We hope we're putting up another proposal together. The CDC has got a project coming, or a grant coming out first of the year. This stuff is, people are becoming more interested in it. The buzzword is directional ventilation. So that's where our project's going there. So indoor air quality for lower hospital-acquired infections. That's the key. So this next little piece really was, I wanted to give some credit out here to Dr. Zhang, because I attended his presentation and he just said some things in there. In fact, I remember him over here where he went, we need to work together. And that whole, what he was explaining is that you need to not just be worried about your sanitization, you need to worry about your HVAC and integrating it into the architecture. Everybody works together to improve this, not individually. And so I said, okay, well, I'm going to try that for our ideas here. So okay, here's my sanitizer. It's in this room. This is like a typical size living room. It's like 14 by 18 or 12 by 18, something like that. And then we did some work a few years ago at University at Buffalo. And we did some CFD simulation, and you see I tried to lay this on top so they looked. And so here's this thing running. Here's the air coming out. You see it goes flat against the ceiling, and it comes all the way across the ceiling, then down the other wall. So that's the basis here of moving the air. So that's where I want to put the people. I want to put the people where they're getting the cleanest air. So how can I do that in the living room? I said, okay, I know how to do that. What I'll do in the living room is I'll put the couch over there. So now this air is going to come across the ceiling and it's going to come down. It's going to bathe everybody on the couch. Right? So they're all getting the cleanest air in the room. And if anybody's sick, it's going down and away. And, just like the hospital room. Well, people typically are not going to want to sit there and stare at their air cleaner. So I said, I need to get the people there. I got the couch. That's where they're going to sit. Well, how am I going to get people there? And that's where I'm going to put all the monitors. All right. So you're going to watch football. You're going to sit on the couch. You're going to get the clean air. This is, so you see you've been fooled into this as to where you're going to sit. The TVs on the bottom, or the monitors are for the kids or your wife, or maybe you want to just watch 3 football games at the same time. Whatever it is, you're on the couch. So that was the idea. Now, the big push is energy savings, right? So we want to do heat pumps everywhere. That's the epic thing to do, right? We want to do that. So I guess I've gone to. So the idea here is I'm going to put the inside unit of a mini split up there. So I'm going to take this air that I've just sanitized. I'm going to put it through the heat exchanger. And now not only do I have the air coming across the ceiling, it's also been conditioned for heat and cooling at that point. That allows me to move the motor and the fan up there, makes it quieter. And then I can change this bottom unit to be a filtration system. So we can put carbon in there. We can, we can put in actually safety filters or whatever kind of thing you're fighting with a filter standpoint. Okay, so what's the outside look like? Well, down at the bottom, I've got a place to bring in the ventilation, outside air, so that can mix in with the system. I've got your typical, mini split on the outside. And if you think about this, if you mounted all those things to something about 14 inches wide, that could be just a section of the wall of your house. So that's that concept with that, which I call the wall of home. So we just design this, we get the architectural folks, we get everybody together, put all this together, put your internet, put up all the characteristics of driving your house there, and there you go. That's where we have. Questions? Thank you.
Thank you.
Yeah.
Ideas.
That's what I'm hoping.
We have a question?
Yeah.
So how are you going to further fund prototyping this and like with SBA, or are you moving forward with doing some prototypes of this?
So I'm in an interesting scenario where my hope is that I can expose the science that I've come up with well enough to form partnerships with companies that have that kind of funding to implement this technology at that level, that have the marketing, the large scale distribution networks already set up. So that's one approach. Getting funding to actually, build the company is kind of tough. I'm looking for in other words, I'm looking for partners and licensees. That's the business model that I have.
I'm not involved in this at all, but it is very intriguing. What you're doing sounds good, and I'm sure there's probably potential partners for you here or Cornell. And what about that company up in, I think it's in Phoenix or Parrish or whatever, that does do air quality treatment with UV? They've sold, there seem to have been, you might know that company, they're very successful. Yeah.
I just,
that, I mean,
just to reach, there is.
For COVID, I guess they've sold, they've given away a lot of units during COVID to schools, and there was a lot of press about them a couple of years ago, and they were I think they're using UV.
Yeah. So one of the things that's happened as I tried to build a business around this is that I talked to a lot of companies that were manufacturing devices that used UVC light. And when they began to understand the difference in the level of technology and they're making money hand over foot because people are buying because of COVID. I have a device that I've demonstrated how well it works. And so I make a presentation to a company and they say, that's really interesting. If we implement or if we begin down this path, we're making it known that ours doesn't. And so there was a lot of that where, why would we develop a new product if what we have is selling well, even though it doesn't work as well. And so that's one of the reasons why the detector came in, is I said, I've got to have a way So if you're just putting a UV light in a piece of ductwork, 24 by, you just stick it in your furnace thing, I can go in there and measure and say, yeah, you're just not killing very much or not inactivating much. So it's really to expose, quite frankly, there was a tremendous amount of snake oil being sold during COVID. Trying to get this across that if you really want to inactivate pathogens at a serious level, you've got to use a technology. And quite frankly, it's more expensive.
Also, I think you're using UVC. Right?
Yeah.
To try to avoid the ozone generation.
No, so yeah, it's kind of interesting. So UVC 200 to 300 nanometer wavelengths, 200 to about 230 nanometer is what they call far UV, and that does generate a significant amount of ozone. In fact, there's a whole technology out there to put 222 nanometer lights in the ceiling. And one of their limitations is they produce ozone. Now, in my devices, I use low pressure mercury vapor, which is 254 nanometers. And the glass is doped to not emit the wavelengths that generate ozone. So in that case, what actually happens is that the 254 removes ozone. So one of the solutions for the far UV technology is to also use 254 because the 222 produces the ozone and the 254 removes it. Like one of the most efficient ways to remove ozone is 254. So it's kind of a balance. And that's a great question.
I have another question. You talk about the direct radiation or reflection.
Yeah.
And also diffuse reflection.
Diffuse, right?
Yeah. Can we change the frequency? Can we change the frequency?
No, not to my knowledge, but I mean,
what circuit kill it?
There are a number of materials. The standard unit uses a very highly polished aluminum. Aluminum is a good reflector of UVC light, but you can only get to about 85 to 88%, but that's specular. The diffuse reflectances, if you do a survey of what do they use for integrating spheres, those coatings, they're ceramic coatings. One of the really good ceramic coatings is titanium dioxide, but that produces a secondary chemistry, so that's not a good one, but it does diffuse reflect very well. There is some sintered Teflon materials that are pretty expensive, but they do a very nice job of reflecting. You can get sintered Teflon to 97%, but it's expensive to a product to make. So I'm studying right now some ceramic coatings that will get me there, because naturally, now that I know that the lab version gives me so much more photon density than the standard, I'm going to replace the standard with a coated liner. As soon as I can find one that I can make and find somebody to make it for me, talk to Alfred, they're the ceramic people, maybe get something going. And to answer your question kind of directly, the approach I have is to work with the universities to get funding, because it's very, very difficult to get funding as a company, but it's less difficult to get funding as a company that goes to the university to do the work. And got very good relationships here with COE and Syracuse University, University at Buffalo I'm working with, Cornell University I'm working with. Tried to get University of Rochester 2 weeks ago, and I didn't make the cut, but But I think that's a good approach to keep going until we get enough science out there and enough proven demonstration to get some companies to take the risk. Large companies don't want to take risk. They want to buy innovations that have already been proven in the marketplace. Very, very different. They're not gamblers. And the mid-size and small companies, they don't have the cash. So it's a tough. I think that I'm in what they call the valley of death, I think they call it. But yeah.
You'll go back, you show the back side of that unit with televisions.
Oh, with the televisions?
Yeah. I have an idea, maybe you thought about this and maybe I'm just not understanding it well. Okay, so you have the inlet coming on the bottom and then the outlet going out.
No, hang on, let me get it back here.
Not a problem.
There you go.
Yeah, turn the back side.
Oh, the backside.
Yep. Cool. Okay. So the inlet's on the bottom and so what's the difference between the inlet, the green box on the bottom, green box on the top?
So the green box on the bottom is where we bring air in to mix outside air with the air that's being recycled in the room. And then it gets sanitized before it goes into the room.
Okay.
And the top is, I just thought, well, I'll make the piping for the mini split short by putting it right on the outside wall. Now, another question is why does the air come out the top? Why don't we have the air go out the bottom? And there's a couple reasons for that. The main reason is that from a fluid dynamic standpoint, the ceilings are usually flat in a building. So when you push that air actually angles up and angles at the ceiling. That top surface acts as a boundary condition, and so you can move the air further across the room.
Isn't that assuming that you're blowing off from a wall as opposed to like in the center of the ceiling, like you see in bigger rooms?
Yeah, this is a perimeter mount device.
Right. Okay. So, is it plausible to basically integrate that into a standard, a standard heat pump type dispenser, or basically build it into it?
I think there's some challenges. I think one of the things, if you look at what a standard mini split does, right, it takes the air from underneath and it takes the air from the top and blows it then down. And so one of the challenges I think of going the other way is you have water condensation. All these mini splits have got a drain line. Yeah, I didn't talk about that, but the drain line comes down to the dog's dish over here. I had to put it someplace. Yeah, anyway. So, but yeah, I think there are some challenges. The fact that you're pushing the air through that in a different direction, but we just need some engineering people that are good at moving air. I can think of a few companies that are real good at that.
Yeah.
Anybody know anybody at Dyson? That would be a good one. Yeah.
I think when you talk about the arrangement, the heat pump efficient, you have air coming out of the bottom, but cool condition of heat pump efficiency. There's a project that Professor Jianshun is working on with getting air into the heat pump system jet bottom. The efficiency of heat pump, the energy.
Oh, the energy efficient. Yeah, he's also studying putting the whole unit at the bottom versus the whole unit at the top.
You need a bottom, jet air, clean air, that. Just different, you can see.
Yeah.
different aspects, or the performance aspects that have the complicated. I think it's the concept of disciplines aspects. Yeah.
Yeah.
It's very changing.
Oh, thank you.